Thanks everyone for joining. I think so. This is the last one. So either you should be so sleepy or so excited. So let's get started. So a little bit about myself. It's actually very little. I am just a staff SDV at EDB and a Postgres hacker. And today my agenda looks like this. The engine starts, the data and memory, the source of truth, death and rebirth, sharing is caring, and we'll have a Q&A at the last. Basically, this talk is all about how under the hood, from the start of the server to the end, and how again it rises up from the ashes, basically crash recovery, and after that, how the things go with the flow, like in between, like the buffer management, the walls, and then the physical replication afterwards. So this is a whole connected journey throughout this. Yeah, let's get started. The engine starts. So what happens exactly when we run pgctl start? Pgctl is one of the Postgres binaries, which is we have so many binaries like initdb and pgrewind, those stuff. So pgctl is one of them, which helps to start, restart, or stop a Postgres server. So when we hit start, the do start API will be called. Then the start postmaster API will be called inside that, which is nothing but Linux fork will be called, which executes the Postgres binary, which will start the actual postmaster process. So this Postgres binary will have the main, which will call the postmaster main, where all the things will start. Like it will initially start initializing the gugs. Like we have all the gugs for changing, doing so many things. So those initialization will happen with some initial boot values. So boot values are nothing but the default values. Let's say checkpointer timeout is by default 5 minutes. So those gugs will be by default initialized with that particular boot values, with all the particular respected values in a particular data type. For each data type of gug, we'll have an C array where all this will be initialized inside this postmaster main. Then if there is a fun fact is that not only using pgctl start, we can start postmaster with using Postgres binary as well, because basically, as in the previous slide, it is basically just executing the Postgres binary with -d option where we are specifying the data directory. So we can even start postmaster using Postgres binary as well. But we have to be careful with all the gugs. We have to make sure it is good and all, because while we are giving the gugs, it will parse through that command line args. So from there also the gugs will be getting initialized. So then it goes on to check the data directory and whether it is actually data directory or just a file. And it will check the permissions for the data directory, and then checks in data directory we'll have a directory called global. In that we have pg control file. It also checks that. It will actually help in so many places. You'll see this frequently, pg_control file. You'll get to know about that in the upcoming slides. Then also it has for each data directory we have one log file, which will help us that each for only one postmaster will be running for one port. So it logs that the data directory is related to that particular postmaster only. Then it also loads the extensions using when we pass the shared period libraries gug, it will just take that value and it will call the particular extensions pginit function, where all the actual work for that particular extension will happen. We'll see what work in further slides as well. And also, if let's say if your extension wants to access the shared memory, you will have this API create shared memory and semaphores API, which will allocate some particular extra memory in the total shared buffers. So that also happens here. Then basically that happens using the hooks. Main reason why Postgres is being famous because is of its extensibility. Extensibility comes through hooks, where every extension can connect through the flow by just using multiple hooks. We have so many hooks for each level, executor, planner, and for every we can connect through that hook and change the flow of the whole execution of entire server or the use case. If I just talk about one subject, I might just divert. So I'm just coming back. That's why I highlighted. This is not for you guys. This highlightation is for me so that I can't distract. So next I will talk about server loop, which is the function where postmaster lives. Because if the postmaster exits that loop, that's it. Server is down. Server loop is an infinite loop where we'll have the latches set for particular request. We'll have so many latches. Previously, it used to be until 15 or 16, I guess, where we'll have this select Linux function, which will be just waiting, sleeping on until any request comes. But this has been changed using the latches recently. So where we'll get the signals to that latch, and it will be waking up through that loop, because if not, it will be continuously just waiting if the requests are not coming to that latch. So there is other thing called background process. If let's say if you want to run, if a user wants to run their own code, extension has multiple use cases for running extra workers, background workers. For that, we'll have launch missing background process. Launch missing background process will be actually starting it will check whether checkpointer is running. If not, it will start. If BGRator is running, it will start. As you can see, these are all the child process. In 18, we have the new process, IO workers, which was introduced by asynchronous IO. Basically, this IO workers will do the reads ahead so that the idle will not be taking up all the load. Then the checkpointer, it will help us maintain the cleaning up the PG underscore wall, where actual walls will be present. It will be removing the old walls which are not needed until it will keep on doing checkpoints, where until this point, if the pages, it will write all the dirty pages to the disks, making sure that the data is consistent until this point. So if data is there into the disk, we don't need the walls, so it will just clean up so that the disk is free for new walls. And also checkpointer will do cleaning, as I mentioned, dirty buffers. It will flush the dirty buffers from shared memory to disk, so that new pages can be read into the shared memory. So, and there is another checkpointer activity which I recently came to know. Let's say if you run vacuum full or a cluster, which is actually currently being renamed as repack in PG19. So if it is run, it will just remove the relation pages directly by truncating into F truncate, so the OS gets that pages memory quickly. So, but the files will be still there. We call it zombie files because the OID file name will be there, and it will be with 0 bytes. So it is still there. It is quite annoying. So checkpointer will, whenever checkpointer comes for, let's say, by default 5 minutes, it will remove those zombie files as well. Then comes the background writer, which also helps the normal backends to offload some work, like it will keep on flushing for every 200 milliseconds by default. This is also by default 200 milliseconds. We can change it using background timeout gug. Then comes the wall writer, which will write the wall buffers from the shared memory to disk. And auto vacuum launcher will periodically run the vacuum on all the tables. And logical replication launcher, which will help in logical replication process, where it will start for each subscriber, it will start a new apply worker. Next, where we'll have this all processes are being start when the postmaster itself is starting. Basically, these all are by default child process, but there are some process which are either additional process we call them, or on-demand process, like backend process, which actually handles the user queries when a user writes a query in the terminal. So those are called backend process, and background workers are the process which executes the user code. Let's talk about them more. Basically, every process goes through this API called postmaster child launch function, which will for each backend we have some backend type enum. So let's say checkpointer, we have checkpoint, basically it's an enum with that particular name. So we can identify each process using that backend type. For each backend type we have particular main function. So because each process has its own work to do, so each process has its own main function. For let's say checkpointer, we have checkpointer main. So it has its own work to do. So this postmaster child launch is the common route to start every process. Then the backend process. The backend process by default, it will be like the postmaster will be listening on localhost by default. That is listen addresses is the GUC with default value as localhost, which will be listening on to all localhost for requests coming up from the clients. So whenever a client connects using PSQL binary, the PSQL will try to connect using libpq. libpq library is underneath. It's all about sockets, which is using Linux APIs like connect, receive, send. This all functions will be used. libpq has extra messages which will be used in wall sender replication as well, which in further slides we'll get to know them. Then comes the background workers, which I told, which will run the user codes using PG init for every extension. Whenever we create an extension, we have this PG underscore init function where all the extension code goes. In that we have this API register background worker, which will just add that worker into the big variable which is used by postmaster background worker list. As you can see, into that list it will be added. So when the postmaster is started, there will be a funny function name. It is maybe start BG workers. So actually it is not maybe, it actually starts if extension is there in the shared preload libraries. When, as I told before, shared preload libraries is the GUC. When if you give that particular name, it will search for that particular extension's binary and it will run this PG init function of that extension, and in that we'll have the register buffer, which will add that particular request of adding worker background worker to the background worker list. And the postmaster, when it is running, it will come through this maybe start BG workers, and it will start the background worker. And this is static. It is not dynamic. It is not on demand. So for that we have another API, register dynamic background. Well, we don't need to restart the server for that. We can just use that, and on demand while server is running, the background worker can be started. Then comes the request via signals. So postmaster receives so many requests that any other I couldn't find any joke for this, sorry. So many requests for postmaster that, like, as you can see, signals. These signals are Linux. We can also use kill command, kill -l for each signal. Let's say sigint, it is the -2, kill -l 2 with the particular PID. Kill -l will give all the numbers for this particular signal. So we can just give that ID and give the PID. So this is all internal stuff. You don't need to do this. For let's say this sigint, sigquit, sigterm, these are all embedded into PGCTL binary itself, which we'll talk later. For example, let's say PGCTL, we are trying to shut down the Postgres server. So by default it will be in fast mode. It will send the PSQL process will hit the postmaster with sigint, which is -2 signal, and it will have a handler. Postmaster will run this handler, and it will set this pending PM shutdown request. It is too long, the variable name, equals to true. Then when the server is again running through the loop, it will check if this variable is set. It will call particular function which will do the actual action, which we'll talk later. Here, let me just bring some water. It is just for my anxiety. I'm just drinking. There's nothing. So thank you. Data and memory. So the fetch. So how actually when a page is being read, what happens? So before that, what is page? It is not the book page. It's let's say we have data which is actually stored in Postgres as in blocks or pages or buffers. So any name is same actually. So for each table file, we'll have 1 GB segment. If that data is exceeding that 1 GB, it will go to the next segment. In that 1 GB, we'll have 8 KB blocks pages. When that page is being read, it goes through this API, read buffer common. So it is a common path for this reading purpose. If by default, if the buffer has this page, it's great, we'll pin it. So what is pinning? So pinning is nothing but we are saying to other process which evicts the buffers from the shared buffer, so that other process can bring the new pages into shared memory. So we are saying some other process are still using it, so don't evict it. So don't evict is nothing but don't remove from the shared buffers to the disk. So pinning will do two things. It will increase the ref count by 1 and usage count by 1. So what is ref count? Ref count will say that how many processes are currently using this particular buffer, and usage count is nothing but it actually being used. Let's say we are having five processes at a time using. So it will show that this buffer is being used so frequently, so that it is so frequent, so we should not flush it, because if we flush the frequently used buffer, the IO spike will increase. So it means that next time there is a probability that the frequently used page will be again used. So this usage count is important for eviction algorithm, which I will talk here. So eviction algorithm, by default we have this clock sweep algorithm, which will have this which will n buffers is how many number of buffers by default. We have some gug for that, and by default, I guess 16K buffers will be there, 16,328 something buffers in shared buffers, shared memory, and this eviction algorithm, how it will decide which page to send back to disk, because we need to bring new pages if a query asks. So the eviction algorithm decides this by every time it will check whether this buffer is not being referred by anyone. So that comes using ref count, any process. So if ref count is 0, then it proceeds to check the usage count, which if it is 0, it means it is not that frequently used buffer. It is a cold buffer, we can say. So we can evict it. So it is the victim. So it will just evict it, basically flush it from memory to disk. So if what if it is being not referenced by any other process? Let's say ref count is 0, but still the usage count is not 0. Some processes are still using it. It is still a hot buffer in the shared memory. We can't directly flush to the disk. So it will just reduce that count by 1. So the max usage count is by default 5, so that we should be fair with all other pages. So we should not be keeping that number way high, so that some pages will be there into the shared memory forever. So for that, it is by default written in code itself. It is not user changeable count. So it is by default max usage count is 5. So every time let's say the hand will go, it is on 10th buffer, it will check ref count. It is 0. Then it will go with usage count, whether it is frequently used or not. If it is 4, it is being used, so let's move on by reducing 1. So 4 goes to 3, the usage count goes to 3, and just it moves on to the next buffer to check. Yeah, this is the eviction algorithm. And I talked about and this is another buffer access strategy. This is clock sweep algorithm is used throughout the shared memory, but this is another buffer access strategy to read the pages, which is ring buffers, like there are some operations which reads it, not reads, which actually floods the shared memory with so many pages at a time that let's say it's Diwali sale running, and Amazon has so many users hitting because of that sale. So there are so many queries, hot queries, means which are very important. So the buffer is filled with all those important pages. But let's say we need to do vacuum for sure, or some other important like bulk reads or bulk writes, which will flush the shared memory with not so useful buffers at that moment of time. So it will flush the frequently used buffers to the disk. So which is a bad thing. So to stop this, we have this ring buffers, which will be part of shared memory, but it is not entirely. It will be by default, I guess, 256 KB. So which is a private ring shared part of the whole shared memory, where we'll have a circular buffer where these buffers will be loaded. So it is not affecting other buffers inside the shared memory. Now, actually, when I previously talked about dirty write, what is actually dirty? The page is not actually filled with mud or nothing. It's just the page is actually having changes, or let's say we did an insert into particular table. In the table, we'll have this blocks. So we call that buffer which has been done some changes on it as a dirty buffer in the shared memory. So when a backend tries to bring a page from disk to memory, and let's say if all the buffers are filled, it has to do the eviction, because there is no other there is no other way for it. It will find ref count is 0, usage count is 0, but there are some operations done on that particular buffer. So if we just move on and crash happens, it is a problem for that. So it will just try, backend needs to flush that before actually reading a new page into the disk. So it is an overload for backend, because backend is doing its own query, and where it has to do again this eviction and all. So this will be an overload for the backend process. So to reduce this penalty, we have two processes. One of the main process is the BG writer, background writer, which will be running for every 200 milliseconds by default to reduce the write load on the particular backend by flushing the dirty pages. When I say there is a big difference here, not all the dirty buffers, only the least recently used dirty buffers are being flushed by this BG writer, because let's say for every 200 milliseconds it is flushing all the buffers, then the IO is way high. That is very bad actually. So BG writer will be flushing only the least recently used buffers. But whereas the checkpointer, it will be it doesn't care about that. Whenever it comes before that point, whatever the dirty pages are there, every page get flushed to the disk, because it has to make sure that before this point data is consistent, because the data is written to the disk. So then let's move on to the checkpointer. As the one thing is, it will flush without checking any least recently used or whether it is more recently used. It will just flush all the dirty buffers. The second thing is, as I previously told, it will remove all the old walls from up before that checkpoint, so that the new walls come into the PG_wall directory, and also it will remove the zombie files as well. Yeah, and it is previously, I guess I told, it is checkpoint timeout is 5 minutes. Then the source of truth, again a small water break. There is actually a story behind this, why I'm drinking water. During my rehearsal, there is one colleague, Floor. She suggested that just breathe, because I was not breathing throughout the rehearsal. So maybe I'll die if I won't drink. So yeah, next. So everyone, I guess, know what is wall. So, but just for the sake of slide, it is a write-ahead log where all the changes between the operations are being logged into the disk. Whenever a operation is done, before the page is written to the disk, the wall actually hits the disk. Because of the high availability, like main reason is crash recovery. If something happens, we need to recover from that crash using these walls, which I again will talk in the next upcoming slides in detail. And there are other there are mainly PG underscore wall is the location where all these walls are being written, and the backend wall writer, checkpointer, and BG writer are these four processes which will be writing the buffer walls from the shared memory to disk. Yeah, internals of wall. So like every by default in initDB we have this option wall segment, which is by default set to 16 MB. We can change it. So 16 each MB is called as one segment, wall segment. In that wall segment we have 8K pages. Here also we call them pages. Please don't be confused with the pages with the rel files page buffer. This page is wall page, that page is relation table page. And in this 8KB page we'll have the wall. In that wall we have the data. Let's go deep. So this is the first xlog record. Xlog record is the struct which will have all the main information, like the total length of this particular wall, and the transaction ID, and the resource manager ID, and also the previous pointer for the previous wall record, which is actually when I was working on PG Rewind, I came to know this is being used. I was thinking why this guys need location of the previous wall, because walls are sequential, which I forgot to say. Walls are sequential, and we have something called as LSN, which is log sequence number, which will be because these walls are sequence, as the S stands for, so it will be continuously being written. So as we are moving forward, why we need to look back? Yeah, again it is going towards PG Rewind. I will come back here. Then after this xlog record we have header part of where we'll have xlog record block header, which will be mapped to that particular block data one. So each we can map it like this. Header part will be mapped to that block one is 1, 2, 2, and n, where this xlog record block will have the block information such as the fork, is it main fork, VM, or FSM, or init, or then also it will have the ID of that particular block so that it can map. Then comes to the xlog record block image header, which will have the full page image size. Full page image is nothing but instead of writing just the delta, means the change, we'll write whole dirty page from disk. We will write into it as total wall. So we will basically writing whole page as a wall. This is used to solve the torn pages problem. Then comes the compress header, which is basically used to compress the hole between the inside the page. Then the rel file locator, which will actually locate the particular page from the disk. Rel file locator will have three things: table space OID, DB OID, and the rel file number. Table space, as the name suggests, which table space, which database, which rel file number, which rel file segment we need to get that from the data directory. And the block number will help us to, as I told, each rel file has one GB segment. In that we'll have 8 KB pages. So for in which that block number specifies which 8 KB page is it. Then comes the xlog record data header. This is mapped to that last main data block. So xlog record data is decide whether it is a short struct or long based on the size of the main data. If it is less than 256 bytes, it will go for the short one with just one variable in that struct. If not, we'll go with a variable size one. So then the block data will have the information about the heap. Basically XL underscore heap header will be there, which will say that what type of number of attributes it has, whether the attributes are null or not, has null. This all information will be there in that struct. And then the payload, where let's say we did a insert value, particular value, that value will be stored in that particular block data. Then the main data, last one, that will have actual tuple offset, where we need to insert because in that particular page we'll have so many tuples in which exact position we need to insert the data. Yeah, I guess that's what it is. So yeah, can take photo. Yeah, then this is death and rebirth. There is a movie coming on, we can watch on that in December. Yeah, types of deaths. There is clean death, and messy death. Messy with Y. Yeah, and the clean death has where basically clean death is nothing but where the shutdown happens properly, which is a planned shutdown, and the data goes to the disk without losing any data. And the messy death is opposite of it. We don't know whether data is gone to disk or anywhere else. Then let's Postgres, as previously I have shown signals, number of signals. In that we have 3 signals which we can use using the binary -m option, PGCTL -m option, like sigterm, sigint, and sigquit, which is like sigterm will shut down the postmaster with smart mode, sigint with fast mode, and sigquit with immediate. So by default it is fast mode. The shutdown happens in the fast mode. We'll discuss about each of them in next slides. In smart mode, when a postmaster gets this smart mode signal, the clients, well, let's say few clients are running few queries. So the shutdown postmaster will wait for the clients to complete that particular work, then it shutdowns properly. But whereas in fast mode, it doesn't care about the backends and it just shutdowns, which is by default. If you without any -m option, if you do PGCTL stop, this is the fast mode is the default shutdown mode. And then comes the immediate mode, which is basically just to crash the server. Still in the upcoming slides we'll have in-depth discussion on that. And these are the APIs for shutdowns, like pending PM shutdown request is the one which hits every time these 3 signals get signal requested by the for the postmaster. So let's talk about clean deaths first. Postmaster process is running, and we have selected smart mode with -m option in PGCTL. So it will check the PM state if it is run or hot standby, which is basically run means in the primary, hot standby means in the replica. It will first check if any connections are if any backends are running their query, and wait for them, and then stop them using this going to the PM underscore stop backends state. But whereas in the other case, where a startup and recovery case, in that case we don't, postmaster doesn't allow any connections at all. So the shutdown doesn't needs to worry about the clients at all. So it quickly goes to the PM stop backends mode. That's what then comes the fast mode, where it doesn't care about the queries running, or it just kills them and moves on to the PM stop backends state. Then comes the shutdown part, where I previously told that the data will be flushed to disk. This all happens because of the checkpointer process. Let's see what happens here. The postmaster will send a signal to the checkpointer. If it is not there, not running because of some reason, it will start it, then send the sigint signal to the checkpointer. We have for when I'm saying signal, we have a PM signal API for each process. Let's say checkpointer main is the function for that particular checkpointer. We have PM signal which is basically setting that for this particular signal we have this particular API or handler to run. So for sigint we have some handler which will set the variable called shutdown xlog pending, which will do the shutdown checkpoint, which will call the shutdown xlog, which will set the shutdown is checkpoint is shutdown, checkpoint immediate flags, and it will do the checkpoint, which will flush all the dirty buffers from the shared memory to the disk and removes as usual it does all the checkpointer things. And then finally it updates the control file to DB is shut down, specifying that now the Postgres is properly shut down. Then it says my work is done and signals to the postmaster with sig user 2, and this postmaster sets the shutdown request pending true. Then the checkpointer process, which is continuously running, it sees that this variable is set and it exits normally with exit 0. And meanwhile, the postmaster also signals this wall sender that we are done for the day and we need to send whatever walls do you have, send it to the standby, the replica. So let's say it couldn't send all the walls, so it will have some walls in buffer. So it will until the latest wall, it will wall sender will send all the walls to the standby and exits normally. So and the postmaster shuts down. Yeah, that was the clean shutdown. Time is there. Oh, okay. I think so. I'm not even done half. Okay, let's vote. Who wants the talk to continue? Okay, then comes the messy death, where this all is not even needed. It just goes to exit 2, which is basically says just crashes all the processes, and finally the postmaster also exits with the same signal, exit 2. There is one process which dies at last if it is enabled, syslogger, which will log all the activity which is being done. It's like the watcher. Until the last minute it won't die. And oh, spoiler. And then we have, it is not like you won't be killing sitting there and just running kill -9 every time, but the actual messy death happens in real world scenario using hardware failure or OS failure or any segmentation fault or out of memory errors. This causes the messy deaths in Postgres. The Reaper, I get you guys know the reference. Because actually in Postmaster until PG15, this function is actually called as Reaper, which was pretty cool. Now it's changed to a long API, as you can see, with so many underscores. When a child process exits, because it is being forked by the postmaster, the Linux will send the signal whenever a child process exits. The postmaster gets to know, oh, my child has died with this sig child. So the sig child will have a handler which is handle PM child exit signal. So which will instead set this variable to true, which will set let's say if a process like startup process has died normally without any crash, it will it will change that to the it will do its proper work and then dies. Like the startup process work is to check if any recovery needs to be done. If not, it will change the state of the server to postmaster to PM_run, which is saying that now we can allow the connections to the server. Let's say if any child process died, it will cause server crash, which takes us to the crash recovery, where when the server crashes, it doesn't do all this stuff which I clean death does. So when server now the control file comes into the picture, where it will startup process will check whether the state of that particular DB is properly shut down. If not, it in this case it will be DB_in production, means it is not properly shut down. So it will start the recovery process. The recovery process will be how it goes is like in the in the control file we have the last checkpoint. So from that last checkpoint, we'll have that particular LSN will read from that checkpoint record to all the walls are being read. When the wall is being read, it will read that particular related page as previously I have shown in the wall internals. We'll have the information of the page, so we'll bring that page from the disk to memory and do the replay. So we are all missing the fun because all the fun is from here. Let's say we are doing insert and some crash happened, but the insert related wall has been written to the disk. So that's why it is called write head log. So when during the replay, the wall will have the information such as xlog heap insert, which will call that particular redo function, which will do get all that information which I have shown in the wall internals, like which page we have to do and where the tuple should be inserted using the tuple offset. Those redo is done here. Yeah, and as previously I have told, until the crash recovery is completed, the clients can't connect. So it is if the server is not able, it is not online. So it is a big problem because it is clients can't connect. So if you feel as a problem, because I am working on something called as fast crash recovery in Postgres, you can just check that out. Then sharing is caring. Which is nothing but physical replication, where we'll take the PG base backup of the primary and start it where the process is very similar. The startup process starts, it reads the last control file and checks the standby.signal file is there. Oh, then it says it is replica. Then it will start the replay. It is a continuous replay. It is like in crash recovery, it does its thing and just moves, it dies. But in replicas, the startup process will be continuously running until the replica dies, because the new walls will be keep on coming. So the startup process starts, then the wall receiver starts, then the wall receiver will try to read the walls from the last checkpoint, and it sees in the local we don't have any wall. So it just signals the postmaster of the primary. Then you may ask how the wall receiver, which is totally complete node, and in that node it is the process, how does it know the information of the primary? Because we have the primary connection info gug, which we have written, or maybe read by automatically PG base backup minus R option will write into the conf file of the replica. So from there we'll get the information like host port about the primary. So it pings using the same libpq framework which I have talked about. So the standby wall receiver will ping, hey primary, give me the walls from this particular point which I have read from the last checkpoint. So then the postmaster starts the backend. Initially it is a backend, but it is disguised as a backend. Then it is nothing but a wall sender. How it happens is that in the libpq will embed it a message called replication. The wall receiver will embed replication message and send it over to the postmaster of the primary. Then based on this message, it will start a normal backend, and while reading using this process startup packet API, it will, oh, this is replication, so we need to convert this backend as a wall sender. So now it is a wall sender, and whatever the request it particular LSN the wall receiver has asked, it will read from the disk and continuously sends over the network to the replica, and replica will be applying by reading it from the disk again. The startup process of the replica will be continuously reading the walls and doing the continuous replay. Yeah, these are all the references, which is one of my blog also, and the code. And I would like to thank these all contributors for this reviewing these slides. And thank you.